This video is brought to you by mywayteaching.com.
So the property of inertia. So in this particular part, we are going to see this. So we face this inertia or we can say the effect of inertia in our day-to-day life. See, suppose we are standing in a stationary bus and the driver starts the bus suddenly. We get thrown backward with a jerk, isn't it? Why that happens? Our feet are in touch with the floor. If there were no friction, we would remain where we were, while the floor of the bus would simply slip forward under our feet and the back of the bus would hit us. So, if there was no friction between our feet and the floor of the bus, then the floor of the bus would move forward and the back of the bus would hit us. However, fortunately, there is some friction between the feet and the floor. If the start is not too sudden, that is, if the acceleration is moderate, the frictional force would be enough to accelerate our feet along with the bus. But our body is not strictly a rigid body, it is deformable, means it allows some relative displacement between various parts. What this means is that while our feet go with the bus, the rest of the body remains where it is due to inertia. Relative to the bus, therefore, we are thrown backward. So, only our feet, which is in touch with the floor, it moves forward, but the rest of the body, on the upper part of the body, it remains where it is. So, our feet moves forward, body remains where it is, so we are thrown backward in that case. As soon as that happens, however, the muscular forces on the rest of the body come into play to move the body along with the bus. Okay. A similar thing happens when the bus suddenly stops. Friction. Our feet stops due to the friction, which does not allow relative motion between the feet and the floor of the bus when bus suddenly stops. But the rest of the body again it continues to move forward due to inertia. So we are thrown forward in that particular case. So the restoring muscular forces again come into play and bring the body to rest. So this is the case of inertia. So now let us see a very simple problem based on the first law of motion. An astronaut accidentally gets separated out of a small spaceship accelerating in interstellar space at a constant rate of 100 meter per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. So in this particular case, an astronaut is in going with a spaceship accelerating with a constant rate of 100 meter per second square. Suddenly or accidentally the astronaut comes out of that spaceship. So we need to find the acceleration of the astronaut at the instant when he comes out of the spaceship. And even we should assume that there are no nearby stars to exert gravitational force on him. So what is the solution for this? Since there are no nearby stars to exert gravitational force on him, and the small spaceship exerts negligible gravitational attraction on him, the net force acting on the astronaut once he is out of the spaceship is zero. So the net external force acting on astronaut is zero because there is no gravitational force acting on him. So, by the first law of motion, we can say that since there is no external force, the acceleration acting on the astronaut is also zero. Okay, so this is the simple problem. So, now let us see what is the second law of motion. See, basically, the first law of motion refers to the simple case when the net external force on a body is zero. Okay. Whereas the second law of motion refers to the general situation when there is a net external force acting on the body. So, when there is a net external force, the acceleration is also acting on the body. How that acceleration as well as external force are related, okay, how those two are related, that we are going to see in the second law of motion. Okay. So before studying that second law of motion, one of the important concept that we need to know is about momentum. So let's see what is this momentum is. See, momentum P of a body is defined to be the product of its mass m and velocity v, and it is denoted by P. P is equal to mv. So momentum is nothing but the product of mass and velocity of the body. And clearly, we can say that momentum is not a scalar quantity, it is a vector quantity because it is having both magnitude as well as direction. So, let's say some of the common experiences to indicate the importance of momentum quantity for considering the effect of force on motion. Okay, we're going to see some of these simple cases where we are going to see this momentum, the use of momentum. Okay, the first case is, suppose a lightweight vehicle and a heavyweight vehicle are parked on a horizontal load. Say lightweight vehicle means we can consider a small car, okay? And a horizontal, no, the weight, heavyweight vehicle means we can consider a loaded truck. So they both are parked in a horizontal road. We all know that a much greater force is needed to push the truck than the car to bring them to the same speed in same time. So we want both of them to move with the same speed. At that time, what is needed? A greater force is needed to push the truck than the car, isn't it? To bring them to the same speed in same time. Similarly, a greater opposing force is needed to stop a heavy body than a light body in the same time if they are moving with the same speed. Isn't it? You just assume that both are moving with the same speed. Now we want to stop both of them at the same time. At that time, a greater force is needed for the heavier body and a lighter force is needed for the lighter body. Isn't it? This is the first case. So let us see the second one. If two stones, one light and another one is heavy, are dropped from the top of a building, a person on the ground will find it easier to catch the light stone than the heavy stone, isn't it? It's a very common experience. The mass of the body is thus an important parameter that determines the effect of force on its motion. So, here mass is very much important, which decides the effects of the force on its motion. Okay, now let us consider one more case. Speed is another one important parameter to consider. A bullet fired by a gun can easily pierce human tissue before it stops, resulting in casualty. A bullet which is fired from by a gun can easily pierce human tissue before it stops, resulting in casualty. The same bullet fired with moderate speed will not cause much damage. Thus, for a given mass, the greater the speed, greater is the opposing force needed to stop the body in a certain time. Taken together, the product of mass and velocity, that is momentum, is evidently a relevant variable of motion. The greater the change in the momentum in given time, greater is the force that needs to be applied. If the change in momentum is greater the change in momentum, then greater is the force that is needed to stop it in the opposite direction, isn't it? Okay, let us see one more simple situation. A seasoned cricketer catches a cricket ball coming in with great speed far more easily than a novice who can hurt his hands in the act. You have seen these type of things, isn't it? One reason is that the cricketer allows a longer time for his hands to stop the ball. As you may have noticed, he draws his hands backward in the act of catching the ball. The novice, on the other hand, keeps his hands fixed and tries to catch the ball almost instantly. He needs to provide a much greater force to stop the ball instantly, and this hurts. So the conclusion is clear. Force not only depends on the change in momentum but also on how fast the change is brought. So the same change in momentum brought about in a shorter time needs a greater applied force. In short, greater the rate of change of momentum, greater is the force. So force not only depends on change in momentum, it also depends on the speed at which that momentum is changed. Greater is the speed or greater is the rate of change of momentum, then greater is the force which is required. So we can see the example of this cricket ball in this particular picture. Okay. Force, it not only depends on the change in momentum but also on how fast the change is brought about. A seasoned cricketer draws in his hands during a catch, allowing a greater time for the ball to stop and hence requires a smaller force. Okay. Observations confirm that the product of mass and velocity is basic to the effect of force on motion. Suppose a fixed force is applied for a certain interval of time on two bodies of different masses. Okay, fixed interval of time, and a fixed force is applied on two bodies of different masses. Okay, initially at rest, the lighter body picks up a greater speed than the heavier body. However, at the end of the time interval, observations show that each body acquires the same momentum. Thus, the same force for the same time causes the same change in momentum for different bodies. Okay, same force at the same time causes the same change in momentum. For different bodies. Okay, same force for the same time causes the same change in momentum for different body. This is a crucial clue to the second law of motion.